Welcome back to Math That Matters. And we want to start today by just a quick review of simple versus compound interest. There's a nice graph we'll show here on the screen, and we've got it on the board so we can keep referring to it. But what we want you to understand is how the simple interest just grows linearly. Nothing special happens the longer time goes, right? It's just, it's interest, it's cool. But with compound interest, that graph really changes substantially over time. And when you get to having a 20-year problem, you've got a real significant difference, all right? And where we left off in our last class was an example of this compound interest. And if you remember, this was Nate's first son, his third child, Noah's hypothetical college fund. It's hypothetical because I don't think Pete did this because he didn't have that kind of money.
No, I don't think I put any money away for him. So.
But if he would have, this would have happened. If you remember, our goal was to get Noah $100,000 in 16 years for his college fund. And we're going to assume 8.5% interest compounded monthly. That's what this notation means. And we solved this problem already. And here's a little visual of it, right? What we found is that you would need $26,000. That's how we solved the problem. And if you put that $26,000 in and wait 16 years, you would have $100,000 that came out. And here's a little graphic showing that the whole pie is 100,000, and it's a relatively small portion of the graph coming from Pete and Amy. Now, there are a couple of takeaways from this example. I think the first one is that Noah's not going to college.
No, he is next year, but not by this route.
Yeah, what is this encouraging or discouraging, Pete?
I actually think it may not be possible, but it's very encouraging because look at how much $75,000 or $74,000 I didn't have to come up with. So
that's right. In fact, this is our first pause and think of the day. Pete just calculated the interest real quick. It's probably because he's a math professor and he's real smart. He just kicked it out. We want you to pause and think, because we never actually calculated the interest in this problem, right? So we want you to take a second and solve for the interest earned in this scenario. Give it a crack. Okay, Pete, our challenge was that they would calculate interest, and you just did it a second ago in your head. I have a question for you. When I think of interest, I think of I equals PRT. Is that the calculation you used to come up with a number?
No, I didn't. I just think about the difference between what I start with and what I end with.
Beautiful.
Because if all I have to do is put in $26,000, but I end up with $100,000, then the difference is the interest. So that's a little bit easier than this way.
I love it. And that's the definition of interest we want you to camp on. Interest is the difference between what you end with and you start with. Now, for fun, Pete, if they would use this formula, they would get $74,000.
I don't think so.
But that's interest.
Yeah, but that's simple interest.
Exactly. Okay, beware. Just because this is the formula for interest, and it is wrapped up in here. This formula is being used, but over and over and over, right?
It is.
Yeah, so again, the idea is we can't use this in a compound interest problem. The only way you can get to interest on a compound interest problem is to compare the beginning and the end, the way that Pete did.
It's much easier that way anyway.
It is, and it's a more intuitive understanding
Sure.
of it. Okay? All right. Oh, thanks, Pete.
Gotcha.
So we are going to now jump into another example because there are two lessons. One lesson is that this is a lot of interest, but I think another lesson is that this is a hard way to save money. I mean, who has $26,000, especially when you have a 2-year-old?
Yeah, because you're kind of young in your career.
Yeah.
You don't have much money.
So I guess the question is there another way to reach one of these big, important savings goals? Because if this is the only way, as exciting as this is, it might be unattainable, as you said.
Sure.
And the reality is there is another way, Pete, right?
Yep.
We're going to draw it up. So stick with us here. So probably a little more realistic and useful way to reach these big savings goals. I still need to have the college fund, but instead of one big lump sum deposit at the beginning, we are going to go ahead with these regular, repeating, smaller deposits all throughout the 16 years in the hopes that together with the interest, they will get us somewhere close to our $100,000. We may not get to $100,000, but if we can't do this, it doesn't matter. And if we can do this, it's a useful scenario. So I guess the real question is, Pete, how would we attack this? And before we explain that, I think we want them to think about this. I want you to pause for a second and think how would you find the future value of a whole bunch of regular deposits? Let's just say you were going to do it every month for 16 years. Okay? So once every month for all 16 years, you're going to put some money in this account. How would you find the total future value? Would you use the same formula? Would you use a different formula? Pause and think and try to scratch out some effort at that. All right, well, I don't know what you came up with, but Professor Pete, how would you attack this problem? Would you use this same formula for compound interest?
I think the answer is yes and no. I mean, the idea is right. So I know I can't put in that much money, maybe it's $200 or something, but I know the money that I put in right now at the beginning, that money would grow according to this compound interest formula for 16 years, and it would be at least a part of my total.
Okay, so I'll call this initial P1.
Yeah, principal one, and then the next month.
That would be some amount of money, right? Not $100,000, but something.
No, it'd grow. The next month I'd put in some more money, maybe P2, and it would grow according to compound interest. And of course, I would have to be really careful because the time would be 1 month less than this time. But
yeah, this isn't going to be the same for both calculations, is it? But that's okay.
Yeah. So we're just kind of looking at it, and I'd actually have to do that every single month.
Wow.
I'd have to figure out what that month's payment grew to in, well, it wouldn't always be 16 years because the time would get less and less and less.
So this is why the answer is essentially, as you said, yes and no. Yes, and that I'm using this formula. This is a compound interest scenario. Each of these principles is growing at compound interest, so there's only one way to calculate it. This
yeah,
is it.
well, in mathematicians, what we'd do is we would create this sum, and we would add all these things up algebraically. We'd kind of put them in a nice little package and simplify it, and we build a new formula.
Yeah, that sounds complicated to me. So let's just this sounds onerous, but it sounds doable to me, Pete.
I mean, for
So,
you can do anything.
Yeah,
Neal.
so I think that's kind of everything they need to know. Let's just jump in and do the problem.
Okay.
Let's give a real life scenario because we still want Noah to go to college. What do you think about? Could you guys bite off $200 a month? Could we try that? Could you deposit $200 for Noah's sake?
Yeah, for Noah's sake.
Okay, $200
Yeah.
bucks a month. So what we're going to do is we're going to try to figure out if you do $200 a month for 16 years, how much money Noah would have at the end
Overall,
of time. Okay,
the
let's
sum
go.
total,
Hope you
okay.
got some good time today. Okay, Pete and I spent a little time to get this set up, but this is all we got to do. This is going to be exciting. It is a lot of calculations. In fact, Pete figured out that there's 192 calculations because 12 times a year for 16 years, right?
That's how many pay periods there are.
So Pete, this would be the future value of that very first deposit. It's $629.71.
That's going to be a part of what we need to end up with.
So he's not going to college yet, at least not this
or
college.
ever, if that's all we do.
Okay, but then for the second deposit, this one right here, it's still $200 a month. It's still the same interest rate, and it's still 12. But this changed, Pete. Tell me about that.
Yeah, so we would only multiply by the multiplier one less time than before because a month has surpassed, and this money is in the bank for 1 month less than this money.
And if you remember, we defined this variable as the number of times it compounds.
Yep.
This one compounded one less time than this one. F3, same thing, 190. And you'll notice, Pete, that this is going down a little bit.
Yeah.
Does that make sense to you?
It makes a lot of sense to me.
Why?
Well, if you think about it, you're investing it for less time, right?
The same amount of money.
And time is money, right?
Same amount of money at the same interest rate, but for less time.
For less time.
Okay, a little bit. And then this is going to be too tiring, so let's just skip about 190 of them. And let's go to the very last one. The deposit you made 1 month before Noah turned 18, $200, 1 plus 0.085. It had 1 month to compound. And look what it earned.
I earned $1.42.
Okay. Hey, nice job.
Well done.
Okay, congratulations. But that's part of that end, all right? So then how would we find the total amount of money at the end of all of this?
If we did all of this and we added up what each deposit turned into over the course of its lifetime in this investment, if we added up all of that, what would it add up to? Did you do that math?
I didn't. That's too many calculations. There must be another way, Pete. Do I got to do this on every problem?
You'd probably like to.
No. All right. There is another way, as Pete said. Mathematicians, this is what we call the mathematicians and the big guns, and they take this idea and they coalesce it and combine it into another formula, right, Pete? And I know you're waiting. Now, you can ignore the next couple minutes of the video and just do things this way if you want. So go ahead and do your homework this way. Or you can pay attention to the next formula and get really good at it and avoid a lot of calculations. Okay, here we go. This is what you've been waiting for. This is, I think, our fourth Mathematic finance formula. All right. And it's specifically for this scenario where you have regular repeating deposits occurring over some time. They're the exact same amount every deposit, and they are growing at some interest rate. And Pete, why don't you break down what the different variables are and what they stand for?
Sure. So F is future value. That's what our money is going to turn into. D is the amount of each deposit. It's the same every month or every so often, however.
So it's kind of like our old P, but now there's a lot of them.
Exactly. And you see R over N so often in these because we're taking an annual interest rate and we're chopping it up. Like if this were 12%, but we're getting paid monthly, we're only getting 1% a month. We're chopping that 12% into 12 pieces.
Excellent.
NT is the number of times that we're getting paid.
That's
the
right.
number of compounding periods. And then there's this -1 that seems to keep showing up, or a +1, which is kind of interesting, but comes to be expected at some point. So I think we could take our previous scenario and just plug in all of the inputs.
And it's a very similar formula, right? If you get rid of those two things, it looks like F equals P, 1 plus R.
It sure does,
So it's just a little exaggeration. I do want to highlight again that N in this formula stands for the number of times that a deposit is made in 1 year. It's not the total number of deposits, so it's not 192, it's 12 in this case. If you made deposits every day, it'd be 365. If you made deposits once a year, it would be
1.
That's right, okay? And T is the total length of the time of the scenario. So, Pete, we're going to pop in our numbers here
let's do
to
it.
try to find the future value of Noah's account.
So 200?
$200 a month. 1 plus an interest rate of 0.085.
Over 12
12.
to the 12 times 16 years. I better put parentheses around those.
Yeah, that's right.
-1
Got it?
divided by 0.085 over 12. I better be careful too because I think I'm going to need an extra set of parentheses here. Always and here around the whole top and the whole bottom of the fraction. We've practiced entering this into calculator.
Yeah, they went back to the very first lecture if you need some help. But Pete, you would do this in one shot.
I would type in the whole entire thing at once. Yeah.
Basically, 200 times parentheses, 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 1 plus 0.085 over 12, parentheses, power, parentheses 1216, minus 1.
Close it, divide it,
divided by
open it, close it, close it.
one shot.
You got
if you
this.
need help with that, come see us. We got to get good at this because we're going to do it a lot.
Yeah.
All right?
Did you type this in?
I
Your
did.
Calculator? What'd you
I
get?
came up with $81,249.
That's pretty close. We wanted 100,000.
Yeah,
so
I think Noah gets to go to college actually now again.
I think so.
And again, it's not as great as the other scenario, but we didn't have $26,000.
Right. This is the best we could do, and it actually wasn't too bad.
Yeah. Let's make a pie chart to see how this distributes. Can we do that?
Sure.
There we go. So now, this is tricky because the first thing we do, we know the total pie is $81,000, right? That's the total pie. But we know it's divided into 2 halves, and half is how much we put in. And
Well,
the
is
other
it half or part of it,
well,
right?
part of it, sorry. Yeah,
Sure,
part of it
yeah.
is how much we put in, and the other part is how much the bank put in.
Didn't we put in $200?
I feel like I gave more than $200. I feel like you gave more than $200.
I did give more. It hurt every single month. It hurt, didn't it?
So how would we do that? Maybe
Well-
you guys can think about that for a second. This is a pause and think moment. What would be the amount of money that you started with in this scenario? Now, start in this case doesn't mean here. It means what's the amount of money that you deposited collectively?
How much
Really?
did this cost me?
Yeah, exactly. Great way to put it. How much did that cost you? Go ahead and give that a shot. Okay, I don't know what you came up with, but really we're trying to find how much interest is in that $81,000, which if you remember, interest is the difference between what we have at the end and what we put in. But this is our puzzle right now because we know it's not 200. Pete, how would you crack what this equivalent to principal is in this scenario?
Yeah. How much did it cost me? Well, it cost me $200 192 times. And I think you've got a formula that can help. If that doesn't work for you, like if the idea of $200 192 times doesn't work for you, you can get there. What is
Use this
that?
cool symbol. Yeah,
I feel like I'm in a sorority or something.
that's a sigma. and it stands for the sum,
Oh,
or the
in
sum of all the
mathematics.
deposits. Yeah.
The Greek letter sigma stands
Yeah.
for a sum.
And that's really what the principle is now, right? It's the sum of all of our deposits, and we're going to do 1D times NT because this is the number of deposits
Yeah.
every time.
12 times 16 years.
So 200 times 12 times 16, and I did that calculation. I got $38,400. So our portion of the pie is 38.4. That's almost half, just under half. Pretty close, right? So that's our deposits. And we know how to do this. Now that means the interest is the whole pie, which is $81,000, $249, and I got to take away what we put in. There's the difference again, what we end with and what we started with deposit-wise. And I did that calc, and I got $42,849. Thank you very much to the bank for that gift
Yeah.
towards Noah's education fund, which this is a really cool, think about this. Think if you did this with your kids. Think if you and your spouse decided to start making deposits. And Pete started a little bit late. He started when Noah was 2 years old, but that's okay, right? I bet if Pete would have started 2 years earlier, that graph would look even
a little
better,
different.
wouldn't it?
Yeah. And again, it's not as good of a deal because I ended up having to spend $38,400 to get up to $81,000 rather than spending $26,000 and going up to $100,000. So it doesn't seem like quite as good a deal, but I also didn't have to come up with $26,000 up front.
And is it compound interest or simple interest?
Well, again, those two things are married to each other, but
Yes.
it's in essence, it's compound interest.
It is.
On a
So
whole bunch of different
We're still getting
deposits.
this beautiful thing, right? And because
Yes.
we're at 16 years, we're getting a lot of help here.
Yes.
So
Yep.
I want to end with another Albert Einstein quote. Not only did he say the quote earlier that you're memorizing, but he also said that compound interest is the most powerful force in the universe.
I thought it was love.
Well, he knew about forces. So hold that thought, and we'll see you next time.